So yeah, I'm a PhD student at the Vrije Universiteit, the Free University in Amsterdam. I'll say a bit more about myself in a second, but today I'd like to present a working paper that I'm working on with two colleagues of mine called Bayesian Additive Regression Trees for Cost-Effectiveness Analysis. This is joint work with Thomas Klausch, who is a statistician at the Amsterdam Medical Center, and Johanna van Dongen, who is a health economist at the University in Amsterdam and one of my supervisors. And I do know that, so there's basically two parts to this title. There's BART, Bayesian Additive Regression Trees, and there's cost effectiveness analysis. And I know that there are some people in the department working on each of that, and I'm not sure if there's anyone working on both of them. But in any case, I could hardly imagine a better place to present this at and get some input on some ideas. So very happy that I'm able to do this. First, a bit about me. I'm actually an economist by training, not a statistician. But as it happens, my PhD work just is very heavily on the statistical side of things. And the way that I ended up here is that a couple of months ago, I got in contact with Andrea Gabriel, who some people might still know, who's a former PhD student at your department. And at some point, he just had this idea that maybe I would like to present some ongoing work and see if people find it interesting and if people have ideas, and maybe if some people even want to join that project or the next project. But I'm going to say more about that at the end. But yeah, that's it for the start, I think. We're going to talk a bit about, so again, I think that some people will be somewhat familiar with much of the content here, but then again, other people might not be. So I decided to keep this a bit more high level, give a relatively elaborate introduction to all the topics, and only after that get to what the new contributions actually are, what we're thinking about doing. So we're first going to talk a bit about what a cost effectiveness analysis actually is, where the data comes from for these analyses, what the BART model is, and then how we might use BART for cost effectiveness analysis. Then I'll talk a bit about a simulation study that we want to include in the paper. And then at the end, a few words about possible extensions, how we could extend the basic framework that we have now. So I think in regular medical statistics or epidemiology, the situation is typically that there are two treatments, and we want to know which of these treatments is better. So which on average helps the patients more, which has a positive average treatment effect, and that is the treatment that we should implement for a given patient population. And the cost effectiveness analysis is very closely related, but there we just add a second dimension to it, because there we're not just interested in how good a treatment is for the patient's health. We're also interested in how much that treatment will cost us, and that is in the sense of how much will it cost society as a whole. Because you can imagine if you keep implementing new medical treatments which are only marginally better than available ones, but are much more expensive, then the healthcare system will go bankrupt relatively quickly. I mean, the NHS in your case does cost effectiveness analysis for, I think, pretty much every medicine. I think that's a precondition for them to be used at all, if I'm not mistaken. Situation in the Netherlands is similar, and in many other European countries. So it's become a very, very important part of the regulation of medical treatments. What I would call the treatment effect on costs should actually be, that is the average treatment effect, it's a bit unclear here, tau C, and the treatment effect on QALY, tau Q. That will come up a lot in the rest of the presentation, so I'd just like to clarify that for now. And if we know these two things, then under certain circumstances, we can make a decision which of the two treatments we should implement. So if one treatment is more effective, so tau Q is positive, and the other is less, and is also less expensive than the other one, so tau C is negative, then I think the decision on which treatment to implement is relatively straightforward because the new treatment, yeah, it's more effective, it's less expensive. We clearly should prefer that treatment, the new treatment, over the old one. On the flip side, if the new treatment is less effective and more expensive, then we clearly should not implement that. The difficult situation arises when one treatment is more effective and also more expensive than the other one. And that's a quite typical situation, because you might have a new innovative treatment, which is somewhat better than older available treatments. But at the same time, the pharmaceutical company which offers that treatment or that medicine will usually ask for a very high price because the development costs were very high and they need to get that back in somehow. So that's a very typical situation. And the role of a cost effectiveness analysis is to then decide how we should make that decision. Give a framework on how to make the decision which of these two treatments we should implement. We do that by introducing what's called a willingness to pay parameter, which is called lambda here. And lambda simply says how much money we're willing to spend in exchange for an additional unit of health. So if typically this health will be measured in QALYs, might also be something else, but a QALY is the most common case. And then it's natural to ask the question, yeah, how much pounds are we willing to spend if we get one QALY in return on average for the patients in that population? Might be 20,000 pounds per QALY, or 50,000 or 80,000. These are the three common benchmarks, generally speaking. And once we have that, we can make up a relatively easy decision rule, which is by simply multiplying this lambda parameter with the treatment effect on QALYs and subtracting the treatment effect on costs. That's called an incremental net benefit. And if that thing is positive, we implement a new treatment. If it's negative, we don't implement a new treatment. And if it's exactly zero, this doesn't really happen. But if it would happen, then we would be indifferent. We could implement either of these two treatments. Can also see this graphically. This is not the prettiest figure, but I couldn't be bothered to make it myself, so I just copied this in from a book, where we have the cost effect on the vertical axis and the QALY effect on the horizontal axis, and then we have this 45-degree line here, which here they call it A, I call it lambda, but it's the same thing. And depending on the value of lambda, this line, it will be flatter or more steep. And if we know the treatment effects of costs and on QALYs, or on costs and QALYs, and we would basically locate that point, that tuple, somewhere in this graph, then if it would fall below that line, that would mean the incremental net benefit is positive, and we implement it. We implement the new treatment. If it is above the line, we would not implement the new treatment. I just include this for completeness because in many textbooks you will find more of a graphical analysis, which is equivalent to this more algebraic thing we have here on the left. And there also is this thing called ICES, or an ICER, an incremental cost effectiveness ratio, which some people may have heard of. That leads to the same. That's an equivalent framework. It will lead to the same decisions. So I will not discuss that in more detail, but it does exist. In reality, we of course don't actually know the treatment effects on costs and QALYs, and we have to instead estimate them. And they are basically, the way I see it, there are three different kinds of empirical studies, or of studies based on data which try to estimate these treatment effects. There are those which are directly based on trials. So when you run a randomized trial, you can, in addition to the information on the medical status of the patients, you can also collect information on costs. And then you can analyze that relatively easily. You can basically just take the sample means. You don't need to do any fancy modeling. And that makes them very reliable. There's no need for statistical trickery. You can estimate these treatment effects in a very straightforward way. The downside is that these inferences are then kind of limited to that trial. and you can't always be sure whether you can generalize that to other patient populations, or if it will stay like that over time, and all these things, because trials typically have a short duration. So these are the downsides. Observational studies are similar, except that there the data does not come from a trial, but rather from a patient registry, from hospital registries, and then these kinds of things. And these are somewhat less reliable because you need to make a lot of assumptions. You need to make assumptions of having all the relevant baseline characteristics of the patients collected. And you have to make assumptions of the statistical model that you use to analyze that data. I'll say more about that later. So they're a bit less reliable. They're potentially a bit more generalizable because you typically have data for a longer period of time. And that data also comes from actual clinical practice instead of a trial, which does not necessarily represent what care looks like in usual care. And I will focus on observational studies. I will talk mostly about that, a bit about trials as well. And then lastly, there is this thing called simulation studies. And the simulation studies in the sense that typically a researcher will combine data from multiple different sources, put them all into a big simulation model, and then simulate synthetic patient data and make decisions based on that. And then you can simulate data for 50 years. You can basically take a patient and simulate the development of that patient over the entire lifetime, which in a way is a lot more relevant because, of course, you want to know the effect over the longest time horizon that is possible. On the other hand, these kinds of models, they rely on very, very strong assumptions because you have to make up a simulation model to simulate this data. And you typically cannot validate it because there are no trials or even patient registries typically which are collected, which have such a long duration. So you cannot validate these models and you're not sure how accurate they actually are. And for that reason, I did not consider this in this study. And it's a bit off topic, but I will not talk about these because it's kind of a different issue to what I would like to discuss. Before proceeding, I just need to get a bunch of definitions out of the way. So in the rest of the presentations, there will be some variables, which are the cost C, the utility score Q. That's typically going to be a quality, but it could also be something else. Then there's some covariates X, which are potentially confounders. And there's a binary treatment indicator Z, which is either 0 or 1. And then I have this counterfactual notation here, which I adapted from the book by Hanan and Robbins, Causal Inference, which some people might know, where basically C to the power of, not the power, but it's written like that, C to the Z equals 1 basically means these are the costs that I would observe for a patient if I had given them treatment 1. Likewise for treatment 0. And then in the real world, when I actually collect data on patients, I observe one of these, right? If the patient received treatment 1, then I have observed C to the Z equals 1, likewise for treatment 0. But I can never observe both of them, only one of them. And then the treatment effect, tau C, is simply defined as the average counterfactual cost under treatment 1 minus the average counterfactual cost under treatment 0. And then, well, if we have a trial, then we can just collect a bunch of data in that trial and basically compare sample means to estimate the treatment effect. If the data is observational, then the treatment and the baseline variables are typically not independent. But we can make the additional assumption that if we condition on these baseline covariates X, then the treatment is actually conditionally independent of the counterfactual outcomes. And it's of course a strong assumption, but I think often it's approximately true. We can maybe say we measured the most important confounders, and thus we may assume that if we condition on them, then the treatment is almost independent of the covariates. And we can then use that fact to estimate our treatment effects, even though there was no randomization. Where we simply say if we want to know the average costs under a certain intervention, we simply average we we average the average costs over the distribution, over the population distribution of the confounders. And that will actually give us then an estimate, or that in this case not an estimate, but that is then the average costs under that intervention. This is all very vague. All the details can be found in the book that I quoted here. These are just the most important results. And then once we actually collected some data and we have some kind of estimator, which is this FC hat here, then we can just plug that in to the empirical sample that we have observed and just use that to estimate our treatment effect. So we treat the sample of the covariates X that we have, we just treat that as an estimate of the population distribution of the covariates. Then we just plug in our estimator and then we get an estimate for the treatment effect on cost. The definitions for Q are exactly the same, so I'll not go through that again, but it works in the exact same way. This I will skip, I think, in the interest of time. So it's in cost effectiveness analysis, it's usual practice to not estimate these two treatment effects on costs and quality separately, but to estimate them jointly. And there's a reason for that, which I tried to sketch here. So if you suppose for now that there's actually randomization going on and we don't need to condition on the covariates, then as most people are probably aware, we can just estimate these treatment effects by taking the sample means in each treatment group. So C1 with that thing over it, that's just that bar over it, that's just a sample mean in treatment 1, the same for treatment 0 and same for the qualies. And then we can just take these estimates, these point estimates, and plug them into the incremental net benefit formula, and then get an estimate for incremental net benefit. And that's all well and good, but the important thing is that the distribution of that incremental net benefit estimator depends on the covariance between the two estimators for the treatment effect on costs and the treatment effect on qualies. This is all derived in the paper by Nixon here. I'll just present the results. So you can either work with the central limit theorem, or you can assume a bivariate normal likelihood that will lead to the same results in this case. And then you can relatively easily show that the distribution of the INB estimator is normal, and the variance of that estimator depends on the covariance between these two treatment effects and between the estimators for the treatment effects. And the covariance in turn of these two estimators depends on the true covariance between the potential outcomes in each group. And that means that we should account for that covariance somehow. We should try to model it or include it in the analysis in some way. If we don't, then we might severely overestimate or underestimate the variance of the INB estimator. And that's of course bad if we want to construct confidence intervals or interpret the standard errors of the estimate and so on. You can also see it graphically here. So if you just look at the left now, at the left column, what I simply try to show here is just an example of what the joint sampling distribution of these two estimators could look like. Where here they have a very strong positive correlation, whereas on the right they have the same mean, the same variances, but a strong negative correlation. And then in the bottom we see that if we actually look at what the sampling quantiles for the incremental net benefit estimator look like as a function of that willingness to pay lambda, we see that if the correlation is positive, the uncertainty about these is a lot smaller than if the correlation is negative. So that means we should probably account for the correlation somehow. Otherwise, we might be misled about the variance of this estimator. With that out of the way, I'd now like to talk a bit about what the usual statistical methods are, which are used to actually perform this analysis in the case where we do have covariates which we need to adjust for. Where I think the most common model in practice, it's what's called the seemingly unrelated regression model, which it's a very common econometrics model. Widely used in practice, has been around for a long time. And it's basically just two stacked linear regressions with correlated error terms. Where we say we assume that we can decompose the costs into its conditional expectation given the treatment and the covariates plus an exogenous error term. Same for the qualies, and then these two error terms are bivariate normal distributed, they're correlated. A very common model, also does work quite well in a lot of cases. But yeah, there are a lot of assumptions made here which are not necessarily reasonable. I mean, the regression function might not be linear necessarily. The error terms might not be normally distributed. Still a good model, but just there are things you can disagree with. But it's a standard of care, standard of use rather. This I will go through rather quickly, so don't lose too much time. There are also some proposals in the literature to use basically ensembles of generalized linear models, where the outcome distributions are not necessarily normal, but rather other exponential distributions. So here's an example that's from a paper by Andrea Gabriel and some co-authors, where they assume that the costs are gamma distributed. The qualies are beta distributed, conditional on the costs, which simply means that the costs are included in the regression function for the qualies. And then they also include hurdle models to handle certain special values. So for example, if costs are 0, that cannot be modeled by a gamma distribution, so you include just an extra component in the model, which tries to account for that. And the advantage of a framework like this is that if you would take that model and you simulate data from it, then the data that you get actually looks a lot like actual patient data, which is not the case with this model, for example. If you would simulate data from this model, well, you get bivariate normal data, which is typically not very reminiscent of what actual patient data looks like. And that's all well and good. I just think it kind of does suffer from the same problems anyway, because in these various GLMs that you include in that model, you still need to specify the mean functions. You need to specify the conditional expectations. And if the specification is wrong, you still might be misled about the actual treatment effects and get wrong estimates. So it doesn't really get rid of that problem, in my opinion. And with that in mind, my co-authors and me, a couple of months ago, we just thought about using nonparametric regression methods for cost-effectiveness analysis, simply to avoid these strong parametric assumptions, which basically all other models kind of have built into them. And an important guide was actually a paper which came out a few years ago. Some people might know it. I think the title is Lessons Learned from the Atlantic Causal Inference Challenge or something like that, but I have it at the end in the references, where basically one group of researchers simulated a bunch of observational data, so with non-randomized treatments, and then invited other researchers to use whatever model they see fit to analyze their data and estimate the treatment effects. And then basically all these other researcher teams sent in their results, what they got, and then the original team analyzed it and saw which of the submitted methods actually works the best. I do realize that these pictures are probably a bit hard to read, but it's fine. Don't care so much about the details here. The main takeaway is that if we look at the models or the methods which perform best on both in both of these graphs, it was lots of different variations of the BART model, so the Bayesian Additive Regression Tree model. And with that in mind, we just thought that this might be a promising candidate to adapt for our use case. And indeed, at least according to the tests we have done so far, it actually does seem to work quite well. Yeah, so the basic idea of a BART model is, like other non-parametric regression methods, is to avoid any strong assumptions on the regression function. And that's achieved to a very specific kind of prior, the BART prior, which I'll talk about a bit later. And our goal here was to basically develop a tool which empirical researchers can use to analyze observational data without having to do too much fine-tuning and too much user inputs, simply because many health economists are not that well trained in statistical methods. So we wanted to give them something that they can easily use without having to think about it too much. Yeah, as shown on the previous slide, the BART models, they seem to work very well in simulation studies. And there also is some evidence that some results regarding consistency and coverage rates. So they seem to work well in finite samples and simulation studies. They also seem to be or have good properties in the asymptotic case. So that's good. These papers that we have for now about BART theory, they're still a bit restrictive in terms of assumptions. But yeah, I'm confident that there will be more results in the future. For now, this I will show this at the end. This is probably the most important paper in that regard. So the basic building block of a BART model is a regression tree, which, yeah, I mean, just for those people who are not familiar with it, the idea of a regression tree is that you partition the covariate space in a bunch of disjoint sets. And then for each of these disjoint sets, you fit its own little regression model, which in the BART case is simply just a constant model. So you just assign one mean parameter to all observations in each of these little subsets, which you can see in the one-dimensional case here in this plot, where the data is basically it's disjointed into 3 separate sets, and then each of these gets its own regression function, which is just a constant. And then the idea of BART is to simply take a lot of these models, these very simple regression tree models, and add them together. Because a single tree, like, it doesn't fit the data particularly well, but potentially if you have a lot of them and just add them up, then that might actually get you a good fit. And indeed, that is exactly what happened. So the idea is you have a regression function f. So that's the conditional expectation of the outcome y, given treatment z and the covariance x. And that is just the sum of m different trees, where each of these trees is what we saw on the previous slide. So that, or rather, it's a function g which assigns to each observation its corresponding mean parameter. So each tree is that's just a binary tree. So that's a tree which defines a partition of the covariate space. And then m, this capital M, that is the collection for a specific tree. That is the collection of the mean parameters in each of the sets in the partition. It's also called leaves. So these these mean parameters are also called leaves. And then G is simply the function which, if you take any input pair, Z and X, then the function G will tell you what mean parameter, what leaf is associated with this input. And yeah, each of the functions or each of the terms in the sum does exactly that. And then you just add them all together. And that then gives you your regression function. We also have an error term, which in the most basic BART model is also assumed to be normally distributed. I'll talk a bit more about that at the end, about possible alternatives to that. A few words about priors and how we do estimation in the BART model. So what I present here is basically the most the first version of default priors for BART, which was presented in a paper by Chipman, where these trees are assigned a prior which shrinks them to be shallow, and which punishes trees which have too many levels, branch out too much. I will not discuss that prior in detail because it's a bit complicated, but I'll provide all the references at the end, so anyone who wants to read about that can do it. The most important thing is that thanks to this prior, each individual tree will typically be quite small. And provide a very, very rough fit to the regression function, so to speak. Then before I discuss the other priors, one thing that is typically done is that you rescale the outcome variable, and the usual, usually it's between 0.5, minus 0.5 and 0.5. Could also be anything else, but that is what's typically done, because that kind of makes the prior specification a bit easier, because then you can simply say to each of these leaf parameters, you assign them a normal prior, where with a standard deviation, which in turn is a function of the number of trees. So the more trees you have, so the higher m is, not sure if I mentioned that, m is the number of trees. So the higher that is, the more aggressively that leaf parameter will be shrunk towards 0, which I think makes sense, because if you have more trees, then clearly each of these trees should contribute a bit less to the magnitude of the outcome. I'm not sure if that makes sense, but basically there is a reason why that makes sense. And this prior then, this 4 is there because it leads to the fact that a priori the probability that the conditional expectation given the covariates lies between minus 0.5 and 0.5 is roughly 95%. So it lies within 2 standard deviation away from 0. And yeah, I mean, that makes sense, right? Because the expectation should not go too far out of our observed values, and the observed values for the outcome we have are rescaled to lie in that interval. So I think it makes sense to shrink the predictions to also lie in that range. And then the variance of the error term, or the standard deviation rather, that's assigned a prior which is kind of a data dependent prior that assumes that the variance of that, so the residual variance after fitting the model, or conditional on the residual variance in the model, should be smaller than the variance that you get when fitting a regular linear model. And yeah, that is simply the prior simply expresses that belief, and thus also shrinks the standard deviation to 0. The estimation method I also will not talk about in detail, but it's simply a certain kind of MCMC sampler where the trees TH are drawn through Metropolis proposals, and then all the other parameters are updated through Gibbs sampling. So quick example of what this could look like in practice. So here we have some simulated data. So these blue and red dots are simply different treatment groups. And we also have the true regression functions, the true conditional expectations for both of these groups here. Both the same color, but I think it should be clear which is which. And well, we see that there's treatment heterogeneity here, right? Because these regression functions look quite different from each other, and at different levels of x, the treatment effect has a different magnitude. For small x is very small. At larger x, the treatment effect is a lot bigger. And this would be not that easy to model with a regular parametric regression, because you would have to make some assumptions on how you would model this parametrically. And clearly this would get a lot worse if you have not only one x, but x is actually high dimensional. Then it would be very difficult to actually model such a heterogeneous regression function in any principled way. Okay, now we'll look at this one. Actually, I think I will also skip in the interest of time. So this is what this looks like after fitting the model, where on the left we simply have 2 posterior draws from the regression functions for each of the 2 treatment groups, and we get this very wiggly discontinuous function. And now you can imagine if instead of 1 draw we just had 2,000 draws, then we could use that to simply collapse them into a mean, the posterior mean, and also we could get quantiles and then treat these quantiles as credible intervals or credible bands. And at least in this example, we see that the BART model seems to do quite well at capturing these heterogeneous treatment effects, which again with a regular linear regression or whatever, that would probably not be that easy to do, or even a GLM. Good, and with all that out of the way, I can finally talk about what we're actually proposing to do. So in a way, it's quite straightforward. We want to combine two BART variations, which have recently been developed. First one is called, or is multivariate BART. So the usual BART model, which is also what I've shown so far, typically has only one outcome, but we would like to generalize that to two outcomes and model them jointly, as explained earlier. And the second method is called propensity score BART, which actually showed up in the graph I showed earlier with all the different methods, which is simply a BART model where, in addition to the covariates, you also include an estimate of the propensity score as a predictor in the model. It's all based on a paper by Hahn and some other authors, which where in that paper they just show that this specification tends to be more robust for to certain confounding patterns, and is just less prone to bias. So the model looks, in a way, quite similar to the seemingly unrelated regression model, except that instead of linear regression functions, we just replace them by these BART functions, and thus thereby allow them to take almost any form that they may. And the idea is that such a model will then be more accurate in observational studies at jointly estimating treatment effects on costs and qualities. That's the basic idea, I think. And once we have estimated that model, we can then go all the way back to the formulas I presented in the beginning, and use that to estimate our treatment effects. But basically, when the MCMC is running, at each iteration, we simply plug the estimates given the parameter values at that iteration, plug these regression functions conditional on these parameter values in the formulas, and then we get a posterior sample, a posterior draw for the treatment effect. And if we do that a large amount of times, then we get our whole posterior distribution for the treatment effects. Emma, how much time do we have?
Maybe 5 more minutes.
Okay, then I will do this quite quickly. So we also wanted to evaluate the new model in a simulation study and compare it to other alternative methods. This is my kind of clumsy attempt at illustrating how the data is generated. Although this is all very preliminary still, so we might still change that. I think I'll skip that for now. This is simply what a typical data set looks like when simulated from that process. Where if we look on the left, the costs tend to be quite skewed and obviously bounded by 0, and most values are quite small. And there are some outliers with rather high values. And similarly for the qualities, and in my experience, this is pretty close to what real patient data looks like. On the right, we see the residuals. So that's simply subtracting the conditional expectations from the observed value. And that's also quite obvious that this is not actually a bivariate normal distribution, not even approximately, which means that that assumption in the model that we're going to use to analyze this data is actually wrong. But maybe it's a problem, maybe it's not. I think that's one of the reasons we want to do the simulation study, to just see how robust the method is to violations in its assumptions. What we're not quite sure about yet is which comparators to include. So we're probably going to include the seemingly unrelated regression model, because that's the most commonly used method. We might also use one of these GLM-based methods. We might include propensity score matching. I'm not sure. I'd be happy to discuss that if everyone has an idea of what's most important. Yeah, in initial tests, BART seems to perform well. Mentioned that earlier, but we haven't actually tried it to anything else yet. So that doesn't really tell us that much as of now. And now a few words about, so we have this relatively basic framework now, which seems to work okay, but there are ways to extend it. So one thing that we're thinking about doing is trying to set up a heteroscedastic BART model, where the covariance matrix of the error terms is not independent of the covariates X, but can actually depend on them. So you, in some covariate regions, you might have higher residual variance than in others, and we would like to model that potentially, because I didn't show it here in the presentation, but one problem with a lot of heteroscedasticity is that the credible intervals will be too narrow in some regions and too wide in other regions, because they're the same width everywhere, which is so the posterior uncertainty quantification doesn't work that well if the homoscedasticity assumption is violated. So that's something we're thinking about. There also exists some tools now to generalize BART to non-normal outcomes. So you could have a BART model where the costs have a gamma distribution, the conditional distribution is gamma. So that's something we were thinking about using, because it's also a bit more in line with a lot of the other literature on cost-effectiveness analysis. And then there also exists what's called a Bayesian causal forest. Some people might know about this, which is a certain kind of reparameterization, which is more robust to certain confounding patterns, at least according to these two papers I know about the topic. So that's something we're also looking into, to maybe phrase the model that way. And that's it. Yeah, so we're writing up the paper right now with the most basic model, the most basic version of it. And then we probably want to make a second paper which implements at least one of these three extensions I mentioned earlier. That we're not exactly sure what we're going to do, and no matter what we're going to do, we probably will have to program our own sampler to do it, because there's no available solution for how to do that yet. And yeah, we'll have to see how quickly we get along with that. And also, I do know that some people in the department have programmed their own BART samplers before. At least I'm pretty sure that's the case. So if anyone would be interested in actually potentially teaming up on this and working together in this project or a project like this, let me know. And yeah, that's it for now. Thank you very much for listening.